Hi, today I'll talk about the work energy theorem that's we have discussed in the class. This is how to derive the work and kinetic energy relations. Okay, let us think that you applied a force on an object which was moving with an initial speed vi, and because of this force, the object moves a distance d as shown in the blue arrow. And when it reaches the distance d, its final speed or final velocity is vf. So the work done is equal to, we know that force times the distance moved in the direction of force. All right, so that's the definition of force of the work done. So now, what will be the relation between the force, the work done and the energy? Okay, so to do these things, let us first calculate the acceleration. How you can calculate the acceleration? Remember that we have the information of vi, we have the information of vf, and we know the distance d or displacement d. So we can calculate these things by, give me a second, it will be loading. Okay, so by definition, work done is equal to fd, and there's no angle involved. Angle is 0, so therefore work done is equal to fd. And from Newton's second law, we know F equal to ma, right? So if you know the acceleration, we can have a expression for the force. To find out that acceleration, we can use the big five equation of the kinematics, which is vf squared equal to vi squared plus 2ad. Vf is the final velocity, vi is the initial velocity, a is the acceleration, and d is your the displacement. Okay, so just give me a second. Where is my laser? Yeah. All right, so now if I rearrange this equation, I like to isolate A. So if I want to do that, what I can do is that I can bring vi squared to the other side. So I get 2ad equal to vf squared minus vi squared, and then divided both sides by 2d. So I will get a equal to vf squared minus vi squared divided by 2d. So this is the expression that I get for acceleration. So now let us focus on this expression, w equal to fd. And if I substitute the f from the Newton's second law, this will become mad, w equal to mad, right? M is the mass, is the acceleration, and d is the displacement or distance in this case. So now I can substitute the expression of A here, vf squared minus vi squared divided by 2d. Look at here. So if I do that, it will become w equal to m times vf squared minus vi squared divided by 2d, and then multiplied by d, right? So this d. And the d here and the d at the denominator cancels each other, because one is at the numerator, one is at the denominator, one is at the top, one is at the bottom, so they cancel each other. So if I now rearrange this equation, this becomes like this: half m vf squared, this is the first term, half m vf squared, and m multiplied by vi squared divided by 2, half m vi squared. And the first expression is the final kinetic energy. Remember, the kinetic energy is equal to half mv squared. So this is the expression. The first expression gave me the final kinetic energy, and the second expression gave me the initial kinetic energy. So this will become kf minus ki, ekf minus eki. So this will be the change in kinetic energy. So work equal to then change in kinetic energy. And that is the And that is your the take from this lecture, that work done is equal to change in kinetic energy. And this is called the work energy theorem. And that's all for today. Thank you.